All right, everyone, here we go. Objective 5.2, polar equations. So we learned about polar coordinates. This is polar equations. And we're going to learn about the difference between each of them and how to convert back and forth from polar equation to from polar equation to rectangular equation and vice versa, okay? We do know rectangular equations already, x equals something or y equals something. We need to understand polar equations, okay? So, first of all, the basic knowledge you need to have is the following. Reciprocal identities. This should be already memorized in your minds. This should not be new, okay? The sine is 1 over the cosecant of theta. The cosine of theta, sorry, let me start again slowly. The sine of theta equals 1 over the cosecant of theta. The cosine of theta equals 1 over the secant of theta. And the tangent of theta equals 1 over the cotangent of theta. Okay, we have to have those memorized already by now. Now, what's new? Well, this is really not new, but this is what we're going to be using. From rectangular to polar, we are already familiar with this equation right here. Okay, this is a rectangular equation. So this is a rectangular equation. How do you know it's rectangular, Mrs. Myers? Because it's an x and a y equals something, okay? And this is the tangent of theta equals y over x. This is also a rectangular equation. So if I want to go from rectangular to polar, this is what we're going to be using. If I want to go from polar to rectangular, then I'm going to have to use this, that the sine of theta equals 1 over r, and the cosine of theta equals x over r. Now, what I did here is I manipulated this to isolate for y. So what I did is I grabbed this function, this ratio, not function. I grabbed this ratio, sine of theta equals y over r. I multiply both sides by r, and then over here it reduced, and I got y equals by itself r times the sine of theta. Okay, so that's what I did here. It's just I manipulated to get this right here. Okay, same thing here. If you multiply both sides by r, you get x by itself, and here we go. So this is what I'm gonna use when I want to switch it from polar to rectangular, and this is what I'm gonna use when I want to switch it from rectangular to polar. Okay. So I know it's kind of confusing. You will see me use it over and over. We'll be okay. So I'll always refer to this. Take a moment to pause this video and write them down. These are the 3 equations that we're gonna be using all the time. Okay? These should always be in our minds because we're gonna use them if they appear. If I ever see a cosecant, a secant, or a cotangent, I need to remind myself, okay, I know what these are. Somehow I can come back to their reciprocal, okay? All right, so I'm going to put this right next to me here, right in front of me. Here we go. I'm converting the following into polar, okay? I want to go into polar. What does polar form looks like? Let me make a big deal out of it. A polar equation is always in the form of r equals something. Okay, let me put these little waves in there. So it's always r equals something, or theta equals something. So that's how I know I am in polar equation. All right, let me make a big deal in a different paper right here. All right, so polar equations versus rectangular equations. In polar equations, it's always r equals something, whatever that is. As long as I can get r by itself, I wrote a polar equation. Or theta equals something. If I can get theta by itself, that is considered a polar equation. Now, what is a rectangular equation? Usually is y equals, you're probably familiar with x squared, because that is a parabola. So that is a rectangular equation. Or x equals y squared. That is a horizontal parabola. We learned that in Math 3. Or y equals 5. Oh, I know what that is. That is just a horizontal line. Y equals 5. So that is a rectangular equation. So how do I know rectangular equation? Because it's always either a y equals or a x equals. Okay, so we are familiar with this. I can do hundreds of them. Okay, 2x plus 1, y equals mx plus b. So that is rectangular equations. Polar equation is always either a r by itself or a theta by itself. That's our goal, is to make them into a polar equation. So now that you have a visual to go with what is the difference between rectangular equations versus polar equations, now we can go ahead and move on. Okay, so when I look at this over here, this is a rectangular equation. It's a special one. You probably don't remember because it was in Math 3 during parabolas in circle. I believe that was Unit 7 in Math 3. But we taught you about this, the equation of a circle, okay? Remember, I'll make a scratch paper right here. You probably don't remember, but I'm going to refresh your mind. If you had x minus 3 squared plus y plus 1 squared equals 64, I would say opposite of h, opposite of k here in this case. So I would be 3 comma negative 1 would be my h and my k. And the radius is 8, because we would take the square root of that radius squared. So we would go and we would find, okay, 1, 2, 3, comma, negative 1, and then we'll count the radius of 8 in all directions, up and down, 8, and then we'll draw a circle. Okay, so that is the equation of a circle. Is it a rectangular equation? Yes, it is. Okay, it's just you're not really remembering that because it's way back in the memory bank. So that's the equation of a circle. Please make a big deal out of this. Say, equation of a circle. Equation of a circle, right? That is the equation of a circle. Okay, how do I transfer from a rectangular equation that we learned in Math 3 to a polar equation? We're going to use substitution. Let me go ahead and grab green, blue here. We're going to use substitution. I know, based on the little formula I gave you, that every time I see x squared plus y squared, I can replace with r squared, okay? I can replace with r squared. Somehow, I want to change this to have a r involved. So what I'm going to do is I'm going to change this because I know that this equals r squared. And I know that this is just 64. As a matter of fact, 64 is r squared. Okay, this is my radius squared. Okay, I want to end up with just r, not r squared. We need to end up with just r. So I will take the square root on the left and the square root on the right. Okay, take the square root on the left and on the right. Since radius only has positive, so I'm only going to do r equals 8. And there we go. I have a polar equation. Okay, I have a polar equation by simply using substitution. Okay, all right, let's try another one. This is a classic example in polar equations. Classic. Every book you open, they'll have this example there. Changing a circle, the equation of a circle in rectangular to this is an equation of a circle in polar coordinate. Okay, all right. Y equals 8. That looks really familiar. In Math 3, we graph that very often. It's just a horizontal line. Okay, y equals 8. That is rectangular. How do I switch into polar? Well, if we look at y, what can we substitute y for? Well, right here in front of us. Y can be r times sine of theta. Okay, every time I see a y, r times sine of theta. So I'm going to use that one. So this is going to be r times sine of theta. It still equals 8 because I did not substitute anything here. I just substituted on the left. Okay, my goal is to get r by itself. So why don't I divide both sides by the sine of theta? It will reduce over here on this side, and we get r equals 8 divided by the sine of theta. That is a polar equation. Polar equation. Okay, if I end up with r isolated, I created a polar equation. So if I was to graph this on Desmos, r equals 8 divided by the sine of theta, I would get exactly the same graph. The graph doesn't change. It is just that now is represented as a polar equation instead of a rectangular equation. Okay? All right, let's try another one. X equals 4. That is a vertical line. How would that be represented in polar equation? Well, over here on our little formulas, we know that x can be substituted for r times cosine of theta. Okay, very simple. Just like we did with the y, we substitute this for r times cosine of theta equals 4. Obviously, I'm going to divide both sides by cosine of theta, so I can have my r by itself. So divide both sides by the cosine of theta, cosine of theta. It will reduce on the left, and we're going to get r equals 4 over the cosine of theta. And that is our polar equation. Okay? All right. One more example. See what we have here. By now you should recognize that this can be substituted by r squared. Let's move this guy to the other side. Okay, let's move this term, negative 10x, let's move it to this side. So let's go ahead and add a 10x to the other side. I know I can substitute this for r squared equals 10x. Okay, I just moved the 10x to the other side, and I already went ahead for in one step, have r squared. What can I substitute this x for? Okay, look at our paper, x equals, so I already have my r squared, 10 times. This can be r cosine of theta. So I substitute this guy right here for r equals cosine of theta. There we go. I no longer have x's and y's. We got to get rid of x and y's. Okay, our goal is to, every time I see x and y's, or x squared plus y squared as a binomial, I can switch it for r squared. So there we go. How do I get rid of this extra r in here? I have two r's in here. I have to only have one r. Well, very simple. Let's divide both sides by r. So over here we'll reduce, and I'll end up with just 10 cosine of theta. And over here we'll reduce by one of the r's, and we'll have r equals 10 cosine theta. So recapping it, I move the 10 over by adding. I substitute the x squared plus y squared, and I substitute the x by r cosine theta. Reduce, and there's our polar equation. Okay? So I'm pretty much using the same exact examples you would see in the book, and there is not a whole lot I can change here when I actually give you problems on the quiz or on the on Edulastic or at notes. What would I change here? This number. What would I change here? This number. Okay, so there's not a whole lot I can change, and the process keeps being the same over and over. Here we go. What did I change here? Well, the number and a little bit. So let's go ahead and subtract this 5 to the other side. I have 3x minus 2y equals negative 5. It's still a rectangular because I have x's and y's. What can I substitute for this x? What can I substitute for this y? Okay, x is r times cosine of theta minus 2, and y is r times sine of theta equals a negative 5. Okay, so that's all I could change. It was the x's and y's, because remember, x equals r cosine theta. I always use this substitution. And y equals r times sine of theta. So I substituted by this right here. So every time I see an x and a y, that's what I'm substituting by. Okay. All right, I have two r's. What I really have here is a binomial, two terms. I have the first term, and then I have the second term. What can I factor out from both of these terms? Well, they both have what I want, which is the r value. Okay, so I have this r here and this r here that we can definitely factor out the r value. So if I factor out the r value, what do we end up with? We end up with 3 times the cosine of theta minus 2 times the sine of theta. If you see now that I want to get r by itself, all I have to do is divide both sides by this parenthesis, this factor right here, which is 3 cosine of theta minus 2 sine of theta, 3 cosine of theta minus 2 sine of theta. We don't care how ugly the function looks like as long as we get our r by itself. Okay, so r equals negative 5 over 3 cosine theta minus 2 sine theta. And again, I was successful in getting my r by itself. Okay? All right. You might want to rewind a little bit and repeat this because that is a nice test question. All right, let's do another one. Now let's go from polar to rectangular. Convert the polar equations into rectangular. And you'll be like, hey, Myers, that doesn't look like polar. Yes, it is. Remember, polar equation is always r equals something or theta equals something. Okay? So I'm going from polar, I want to end up with rectangular. If I want to end up with rectangular, I either end up with x equals something or y equals something. So when I see a theta by itself, okay, I can't substitute anything for it, but let me write it down again. Theta equals pi over 4. So all I did is I rewrote the problem. Okay, rewrite. So all I did is I rewrote it so I can play with it. I can go ahead and apply a function to this angle. Okay, I can go ahead and apply a function, which is the tangent. Okay, I apply the tangent here. Now I have the tangent of theta. It's kind of like if you had, let me go ahead and give a algebra example. If I had x equals 2 and I want to apply a function to it, what function could I apply on both sides? I don't know. I could apply a radical to both sides. That is a function that I apply to the left and to the right. Okay, I could have squared both sides. I could have done the cube root of both sides. So that's when I apply a function to it. That's what I'm doing here. I am applying the tangent function to both sides. If I did it on the left, I better do it on the right as well. Okay, so I wrapped the tangent around here on the left, and I wrapped the tangent around here on the right. Okay, what can I substitute for the tangent of theta? See here, the tangent of theta is a y over an x. So every time I see a theta by itself, I can wrap the tangent around, I can apply the tangent function to it, and then I can substitute for a y over x every time I see a theta. So I can substitute this for a y over an x. What do we do with the tangent of pi over 4? Well, I go find that value. What is the value of the tangent of pi over 4? Look at your unit circle. If you haven't memorized by now, the tangent of pi over 4 is simply a 1. Cool, I'm almost there. How can I get a y equals equation? Well, if you multiply both sides, left and right, by an x, they reduce here, and 1 times x is x. So I end up with the y equals x function right there. Let me give you a visual. I love visuals, so you can see what that looks like. Okay. Originally, here's what we had. We had theta equals pi over 4. Well, if I look at my unit circle, that's what it looks like right there. The angle from here to here, that is pi over 4. How would I represent this without an angle, without an angle labeled at all? How would I represent this? Okay, let me draw the same exact picture. There we go. How would I represent the exact same graph, but in rectangular? Well, if I continue with this graph, that is the y equals x line. So see, this is the rectangular representation of this. This is the polar representation with the angle attached to it. Theta equals pi over 4. Okay, so that is the polar, that's the rectangular. So that's what we did here. We switched it from polar to rectangular. Isn't math beautiful? All right. Let's go ahead and switch it again. Theta equals 5 pi over 6. I know what that looks like, okay? In the unit circle, it looks like this right here. All right? That is that angle right there. Theta equals pi over 6. How do I make this look like a rectangular equation? I represent it as a rectangular. Very simple. We're going to wrap around both sides the tangent function. So it's going to become the tangent of theta equals the tangent of 5 pi over 6. So this is theta went in here, 5 pi over 6 went here. All right? So what is the tangent of theta? Well, I can substitute this for a y over x. What is the tangent of 5 pi over 6? Negative root 3 over 3. Your unit circle never goes away in this class. Okay? All I have to do now is multiply both sides by x. I'm going to multiply this side by an x, multiply this side by an x. It will reduce here. I'll have a y equals negative root 3 over 3 times x. That would be the that would be the rectangular equation for this tilted line over here. Okay. All right. So notice whenever I have a theta, we wrap the tangent around it. We find the value of the tangent of whatever the angle is. And that's the same steps over and over. Okay? All right. What happens if you start with an r equals 4? How do I change that from polar to rectangular? Well, it would be nice if we had an r squared, right? So let's go ahead and square both sides. So r squared, if I square this guy, then I have to square the number 4 as well. R squared equals 4 squared is 16. Well, what can I substitute this so I don't have r's anymore? We want to get rid of r's and end up with x and y's. Well, then this is simply x squared plus y squared equals 16. So pretty much we worked backwards from the first example I gave you. Let's rewind a little bit. The very first example I gave you was, if I have an x squared plus y squared equals 64, that's the equation of a circle. How do I switch it to polar? We did it. We got r equals 8. Well, I worked backwards. I gave you r equals 4. That's the equation of a circle in polar. Equation of a circle in polar form. Now this is the equation of a circle in rectangular form. We just worked backwards. Now let's go from polar to rectangular. I have r equals 2 sine theta. And you're probably thinking, I'm just going to square it, just like she did on the problem here. Nope, don't square it. Because if you square this, yes, looks pretty. But when you square this, it's not going to help you at all. So do not square. Okay? Don't square it. How can I get a squared without squaring? Well, another way to get squared without squaring is multiplying. So I'm going to multiply both sides. Let me rewrite the problem. R equals 2 sine theta. So I'm going to multiply both sides by r. So I'm multiplying by r here. Then I can go ahead and multiply by r here. Okay? So now I have r squared. Wait, am I doing this right? Yeah, I think so. R squared equals 2. R times sine is r sine of theta. I just put the r, I just moved that multiplication factor to the front here. All right, cool. What does this look like to you right here? R times sine theta. R times sine theta. Well, look at your notes. What does it look like? And what can I substitute this guy for? Okay, I can substitute this for x squared plus y squared equals 2, and this can be a y value because r times sine theta is a y. There we go. I'm almost done. Some people say, why can't you divide by 2 and you get a y by itself? I know, but whenever I have an x squared plus y squared, I'm dealing with some sort of a circle. So why don't I just move it over? I get x squared plus y squared minus 2y equals 0. And guess what? We worked backwards. What example was that? Let me find it here. It was this example right here. X squared plus y squared minus 10x equals 0. And then we multiply, blah, 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 blah. We end up with r equals this. Well, that's exactly what I had. R equals 2 sine. And then I worked backwards to get back to this rectangular equation. So I don't know if you noticed by now, I'm just kind of like working backwards from polar to rectangular. All right? We're almost done. This will be less than 30 minutes, I promise. My last one. Okay. If I have a r equals cosecant of theta, holy guacamole, let me rewrite it. R equals cosecant of theta. What do we know about cosecant of theta? Oh, dang, I do know that the sine of theta equals 1 over cosecant of theta. That's all I know. That's all I know. That's literally all I know. Well, then let's go ahead and also think about this, that the cosecant of theta equals 1 over the sine of theta. All right? They're reciprocals of each other. Okay, so why don't we do that? Why don't we substitute this for r equals 1 over sine of theta? Cool. If I multiply this side by the sine of theta, and I multiply this side by the sine of theta, over here it reduces. I get the 1 all by itself. But what does this look like to you? I'll rewrite it, r times sine of theta. Okay, what does it look like now if you haven't recognized it by now? Equals a y equals 1. That is our rectangular equation. If I had to graph that, we usually ask Math 2 kids to do that. It would be right here, Ms. Myers. It is a horizontal line, y equals 1. All right, there we go. So we went from a polar to a rectangular by simply using these right here, nothing else. Okay, so write it down nice and neatly like that on a 5 by, I don't know, whatever measurement you want card, and use this all the time because that's the formulas I used. And we're done. See you guys in class.